Welcome to homework.
So, in this question, we have been given a state of strains at the point on the arm of the components, right? So, the strain that is acting in the x direction, its magnitude is 200 into 10 raised to power negative 6, right? And the strain that is acting in the y direction, its magnitude is negative 300 into 10 raised to power negative 6, right? And the shear strain is equal to 400 into 10 raised to power negative 6, right? And the angle of contact, right, that is equal to 30 degree. So let's start with the solution. Now, the solution for this question is very simple. Now, as you can see that the angle that is given to us, right? The angle at which the element will be oriented, right? So this angle 30 degrees is um, counterclockwise, right? Now, why it's counterclockwise? Because in the theory of this chapter, we agreed that we'll take the angles at counterclockwise and we'll say that they are positive, right? So the angle in our situation is positive 30 degree, right? Now, let's start with the um, further solution, right? So what we need to do is that we need to find out the in plane strains, right? um, of the element that are oriented at the given angle. So for that, what we are going to do is that we are going to use the equation um, 10.5 through 10.7, right? So let me write it a little bit nicely. So that is 10.7. um, 10.7, right? Now what we are going to do is that we are going to start off with the normal strain in the x direction, right? So for that we're going to use the equation 10.5, right? So the strain in the x direction, normal strain, right? So that is equal to the average of the strains that are acting in the x and y direction, right? Plus um, the strain in the x and y direction divided by 2 times cos 2 theta plus uh, gamma sub xy divided by 2 sine 2 theta, right? So we have all the values of these variables, so just plug them in and calculate it. So when we calculate it, we get that it's equal to 2.428 4821, right? It's equal to 4821 into 10 raised to power negative 4, right? And that is approximately equal to 248 into 10 raised to power negative 6, right? Now what we're going to do is that we are going to use um, equation 10.6, right? And we are going to find out the value of the shear strain, right? So for that, we have the equation that is equal to the expression that is equal to the negative um, of the difference of these strains, right? That is multiplied with the time that is multiplied with the sine to theta, right? And over here we have the strain, right, divided by 2 times cos 2 theta. Now again you have all of these values, right? So you just need to plug them in and calculate it. So we get that's equal to 1.1650 into 10 raised to power negative 4, right? And now what we are going to do is that, as you can see, that this is the value of the shear strain divided by 2, right? So we need to shift this to over here, right? So when we'll shift this um, to we are going to shift it to the right hand side, right? So that would become 2 into 1.1650 into 10 raised to power negative 4, right? And this would be equal to uh, 233 into 10 raised to power negative 6, right? So now that we have the value of the strain, a normal strain, and the shear strain. So now we can find out the value of the normal strain in the y direction, right? So that is epsilon sub y dash. It's equal to these strains in the x and y direction divided by 2 negative the strains again divided by 2 times cos 2 theta, right? And over here we have the strain divided by 2 sine 2 theta, right? Again you have the value, so you just need to plug them in, and when you plug them in you get that it's equal to uh, negative 3 negative 34821 into 10 raised to power negative 4, right? And that is approximately equal to 348 into 10 raised to power negative 6, right? Now what we're going to do is that we are going to um, as per the questions demand, we are going to sketch the answer of this problem, right? So let's take a look at that. So as these are the sketches, right? Now in this sketch A, right, this is showing the original element, right? So this is showing the original element. Now this is B, right? Now this is showing the element in the new orientation, right? As you can see that um, this element, it has been lifted right at an angle of 30 degree, right? It has been oriented at an angle of 30 degree, right? Now this is C, right? So this is a show this C um, sketch shows that how the strain deforms the element, right? As you can see that this was the original shape, that is the solid, that the one with the solid lines, right? That is the original shape of the element, and when there is some stress applied over here, so its shape has deformed, right? And this is the D sketch, right? So this is the complete sketch of the problem, right? I have drawn three sketches because it helps you to understand this D sketch a little bit better, right? So that is the main reason. Now, remember that the positive normal strains, right? That is epsilon sub x and epsilon sub y, right? They means the uh, elongation in that direction, right? Uh, Direction with which they're associated with, right? And the the n- negative strains, they means that there is some compression in that direction, right? So positive means that there is elongation, and negative means that there is some compression. Right now, the positive shear strain, right? The positive shear strain, it means that there is some counterclockwise deformation, right? And negative shear strain means that there is clockwise deformation, right? So these are some key points that you must remember, right? That positive strains means that there is elongation, right? Negative strains mean that there is compression, and positive shear strain means that there is counterclockwise deformation, right? And negative shear strain means that there is clockwise deformation, right? So this is your complete solution to the given question.